Hello everyone. In today's session, we are going to see the new topic from the strength of materials, that is the torsion. First we'll see the introduction to torsion, assumptions used in torsion, and then we'll move to the derivation, means torsional formula. So we are going to derive the torsional formula. So for this one, we'll start with the torsion and the torsional theory. Now, torsion means it is a torsional moment. So actually it is a torsional moment, and in that torsional moment, what are the stresses which are going to generate in the material that we are going to see. So consider one shaft which is transmitting power from, this is the shaft which is transmitting the power from one pulley to one gear arrangement. So this is the pulley and this is the gear arrangement. Now while transmitting the power, this pulley is connected to the motor and this gear arrangement is transmitting power to the another shaft through gears. So when this power will be transmitted, then this is the driver and this is the driven. Now driven is connected to another element so that this will oppose the motion, oppose the rotary motion which is provided by this pulley, so that the twist will be generated. Means we can say that this end is rotating and this end is opposing. So when one rotating end and there is one opposing end, so that will come to one condition that one end will be fixed and another end will be rotating. So if we consider along this axis, then this will be rotating in this direction with the applied moment, that is the torque T. So along this direction we can say that this end is rotating, this end is fixed, so this shaft is subjected to twist. During the twisting, this shaft will subjected to the shear stress. Means shear forces will act in the small particles to oppose this torque and it will subjected to shear stress. This condition will occur in the initial stage, because in the initial stage while transmitting the motion there will be the opposition force. So this gear means which is connected to the another system that is going to oppose the motion, so that this condition will be occurred. Means this end for that particular moment, you can say that this end is fixed because it is opposing and this end is rotating. Now for this particular case, to generate the formula, the stress which is generated in this shaft is the shear stress. Now to calculate this shear stress, there are some assumptions that we are going to use in this torsional theory. These assumptions will see after completion of the derivation. So for this I am going to start with the derivation. Now for the derivation I am going to draw the same figure which is shown above, but I am going to show in opposite direction. Means the fixed point I am going to keep on the left side. So this is the fixed end. Along the axis we have applied the torque. So I'll show the torque along this axis. Means this end is rotating, this end is opposing, so that it is subjected to twist. Now consider one line along this shaft AB, straight line AB. This is the initial position. After the twist, after this twist, this B point will shift to the new position, that is B dash. So if I join with the center, then this will shift to new position B dash. If I draw the line of A to B dash, then this will be the angle turned by this line. I'll call this angle as phi along the length. For this purpose, we will consider the length of this shaft as L. So, see, AB is the original line along the length. After the twist, the B will move from B to B dash. The angle turn will be the phi. If you see this cross section, which is a circular, where the radius of this shaft is R. This is the point B. See, this is the point B. This is the center. Okay. And after the twist, it will move to B dash. So, consider a new point B dash. Here, the angle turned in cross section is theta, which is called angle of twist. So, actually, we will see the twist in this cross section and it is represented by angle theta. So, in the cross section the twist is theta, and along the length the AB line is moved to AB dash. But this twist is very small. So, when the twist is small, then we can say that this arc BB dash, we can say that this arc BB dash, here BB dash will be small, so we can consider it as a straight line. BB dash we can consider as straight line. So when we consider this as straight line, then along the length this phi will be the strain which is generated. So phi will be the strain and theta will be the angle of twist. Now to start with this derivation, I'll consider the arc BB dash. Arc BB dash. We can calculate this arc BB dash by using the formula arc is equal to, for any circle, if you want to calculate arc is equal to radius into angle. So I am going to use this formula, arc is equal to radius into angle. So from this cross section you can say that this arc B dash will be R into theta, that is radius into angle. But same thing we consider along the length, then we can say that BB dash actually it is arc, but if the angle is small we can say that arc is equal to straight line. So BB dash, that we can give radius along the length, the radius will be L and the angle turn will be phi. So we can write L into phi. So along the length L will be the radius and phi will be the angle. But as per the Hooke's law, the stress is directly proportional to strain. So here I am going to write stress will directly proportional to strain by Hooke's law. So stress is proportional to strain. So stress is equal to modulus of elasticity into strain. Same thing we can write in case of shear stress. So this is for normal stress. I will write for the shear stress. So shear stress is proportional to shear strain. Okay, and if we remove the proportionality, then it will be modulus of rigidity into strain. So shear stress is equal to modulus of rigidity into strain. Both the formulas are same. This is for direct, that is tensile or compressive stress, and this is for shear. This is the modulus of elasticity, which is material property. This one is also modulus of rigidity, which is material property. But here in this formula we have phi that is shear strain. So from this formula we can write phi is equal to shear stress divided by modulus of rigidity. So I will replace that thing. So R into theta is equal to L into phi. Phi is shear stress divided by modulus of rigidity. Now I will rearrange the terms. So to rearrange the terms, I will shift some of the terms on the left side and on the right side. So transfer this R on the right side. So this will become tau by R, and transfer G and L on that side. So G into theta divided by L. So this is the equation number 1. That is tau by R. Tau means shear stress produced, divided by R means radius, is equal to G theta by L. G means modulus of rigidity, theta angle of twist, and L means length. Okay, so this is the equation number 1. Now as we have talked that in the cross section the stresses will be generated are of shear stress. So here we can see this is the maximum shear stress which is obtained at maximum radius. So if you consider the outer portion here, then here will be the maximum stress. Now if I put the value of R 0, means at O point, then the shear stress will become 0. Means along this radius, if you go outward, the shear stress value is going to increase. And here the tau means tau max, maximum shear stress, R means maximum radius. So from this expression we can write if you take the proportionality, means intermediate point at this point, then tau by R is equal to Q by small r. Tau means maximum shear stress, R means maximum radius, small r means intermediate radius. Here you can take any intermediate point between B and Q. Okay, and at that point the shear stress produced or present, I will call this point, call this shear stress as Q. So in any intermediate point the shear stress will be Q. Okay, so from this expression we can write. I will mark this one as equation number 2. This is the proportionality between shear stress and radius. Now as we have talked initially, in the cross section the shear stress produced is because of the opposing forces which are generated by the different small particles. So I am going to draw that particular case. So consider this is the cross section, and in the cross section I will consider one small point whose area is dA. Okay, the shear stress present here will be Q, means in this small particle the shear stress is Q and its area is dA, and this point is at radius R. Then the force which is acting on this particle will be dF. As we have considered a small particle, so the force value generated will be the small, that is dF. Now from this cross section we can write, from figure we can write shear stress is equal to shear stress produced here is equal to, now stress is equal to force divided by area. As we have considered small area, as we have considered small force, so Q is equal to dF by dA. So I'll rearrange the term to get the force value. So dF will be Q into dA. dF will be Q into dA. Now we can write the value of Q from equation 2. So transfer this small r on the left side, so that we will get the value of Q. So I will put that value here. So dF will be tau into small r divided by capital R into dA. Okay. So I have placed the value of Q and I have put from equation, I have taken it from the equation number 2. Okay. So dF is equal to tau into R divided by capital R into dA. So this will provide me the value of small force which is present in this material. Okay, means in this small area. Now if I want to calculate the torque from this small particle, so torque transmitted, torque is nothing but moment. So if I want to calculate the torque, then the torque transmitted by the small particle will be dt, because the small force is dF. So that torque is nothing but the moment. So how to calculate this moment? Force into radius. See, here we have in this figure force into radius. So dF into R will be the torque transmitted. Now we have the value of dF. Consider this as equation 3, and from 3 put the value of dF. So this will become tau into small r divided by capital R into dA into small r. This is the value of dF. Okay, so we can write this dt is equal to tau r into r, r square divided by capital R into dA. So this is the value of dt. But this is the torque which is transmitted by this small particle. Now if I want the total torque, then we will have to add the torque transmitted by the number of small particles in this cross section. So when you are going to add this all, means I am going to make the summation of all the small torques, so it will become the integration. So integration of dt is equal to integration of tau r square divided by r into dA, and this will provide me the total torque transmitted. So to find out this total torque, I will have to make the integration of the above equation. Now the limit for the torque, when the shaft is not rotating, the torque transmitted will be 0 and the maximum value will be T. Similarly, for this particular area, we can say the area will be 0 to maximum area A. Okay. Now we will take some of the values which are constant outside of this integration. So the maximum torque, it is constant, maximum radius, it is constant. So it is integration of r square dA, and the maximum torque will be T. If I put, then integration will be T, limit T to 0, so T minus 0 is T. So this is the total torque. Okay. Now the value that we have got here, that is r square dA, is nothing but the second moment of area. Here I will write, it is nothing but the second moment of area, SMA, and this SMA is equal to moment of inertia that we have learned in 12th and applied mechanics. So SMA is moment of inertia, that is r square dA. dA into r means area into r is first moment and into r will be the second moment. So this will be the moment of inertia. But the moment of inertia here that we have got is about which axis? that we'll see. Just wait, I'll show you. We are calculating this one about this axis, this horizontal axis. This axis, if you consider, then for this cross section it will be the ZZ axis. So the moment of inertia will get here will be about ZZ axis. So the moment of inertia about ZZ axis is nothing but the polar moment of inertia. So I will mention it as J. J means polar moment of inertia. J means polar moment of inertia. Polar moment of inertia. Now transfer this J on the left side. So T by J is equal to tau by R. This will be the equation number 4. Now the last step of this derivation, just see the equation number 4 and equation number 4 and 2. From 4 and 2, see, in equation 2 tau by R is equal to Q by R, and equation 4 tau by R is equal to T by J. So in both equations we have tau by R. So from 2 and 4 I can write, from 2 and 4 I can write T by J is equal to tau by R is equal to G theta by L. So this is the expression for the torsion theory. Okay, expression for torsion theory. T by J is equal to tau by R is equal to G theta by L. Now this equation will provide you the value of torque which is required, or you can calculate shear stress, or you can calculate the angle of twist produced in the torsion. Now the terms which I will repeat the number of terms. T means torque, J means polar moment of inertia, tau shear stress, R maximum radius, G modulus of rigidity, theta angle of twist, and L is the length. Now after completing this formula, I will go for the assumptions. There are 5 assumptions that we have used here. The first assumption, see, first assumption from this formula I can write. Here we have used the G. G means modulus of rigidity, which is the material property. Means in this shaft we are considering the material property is same in each point. Means this material is homogeneous and isotropic. Means it is homogeneous and isotropic. Second, see the line that we have drawn here, AB and AB dash. Both the lines are straight. Means after the twisting, the straight line along the length will remain a straight line. Okay. Next, consider this plane, means cross section. Before twisting, this plane will remain as it is after the twisting. See, I am going to repeat the first one. Material is homogeneous isotropic. Second, the straight line along the length will remain straight line. Third, the plane before twisting will remain same after twisting. Okay. Now the next one, all the properties that we considered here, that is the modulus of rigidity. This modulus of rigidity or Hooke's law, the Hooke's law is only applicable up to elastic limit. Means the stresses or strains which are produced here are within the elastic limit, So these are the assumptions that we have considered for this torsional theory. So I will summarize the things within a minute. See, when any shaft or any rotating particle subjected to torque, ultimately the other end will oppose the motion, so that it will subjected to twist. This twisting moment is called as torsion. Okay. Now, in the torsion, we'll have to apply the torque. So torque, radius of shaft, length of shaft, angle of twist, and shear strain is going to come. And into the formula, the formula will be T by J is equal to tau by R is equal to G theta by L. Okay, so in today's session we have finished with the torsional formula, torsional derivation, assumptions used, and introduction to torsion. In next session we will solve some of the problems from the torsion. Thank you.